Hello, and welcome to the Satellite Image Deep Learning Podcast. I'm Robin Cole, and it's my pleasure to present another technically focused episode in the series. In this episode, I catch up with Ryan Avery to learn about the machine learning workflow at Development Seed. Ryan is an expert in developing machine learning-powered services for processing satellite and camera trap imagery, and he is deeply passionate about leveraging machine learning to enhance environmental outcomes and improve livelihoods. In addition to his work at Development Seed, Ryan has made significant contributions to open source. These include a comprehensive 2-day geospatial Python curriculum, an image segmentation model service, and a torchserve deployment of Megadetector for wildlife monitoring. Our conversation was highly educational, and I hope you enjoyed this episode. Hi Ryan, how are you doing?
Great to be here, Robin.
Thank you. So I've been a big fan of Development Seed, and you're obviously working there as well. Do you mind just giving us a quick introduction to the company and your role at it?
Absolutely, yeah. So Development Seed is a small to mid-sized company, about 50 folks, 50 engineers that work on geospatial solutions that span from making it easier to access and process geospatial data, so both imagery and vector data, as well as we have a GeoAI team. So I'm a machine learning engineer on that team. We do everything from helping folks with data annotation for creating custom machine learning models to training those models, evaluation, and then helping them serve those models to users. So yeah, we kind of like span all pieces of like the geospatial product development around platform development, as well as like the machine learning model development.
Right. And one of the things I did notice about Development Seed, you're very open around both the work you do and how you do it. I noticed you almost got 500 repositories on GitHub, which is just an incredible number, for example. And you've obviously co-authored or authored many of the blog posts from the company. That was what sparked this conversation, of course. You published a 3-part series on your tool stack, and I thought it'd be a really exciting opportunity just to talk through what that tool stack looked like, and also to get an idea of the arc of how an ML project looks. So perhaps we could start at the beginning. Where does a project begin?
Absolutely, yeah. So depending on the project, it might be less of an arc and a bunch of zigzags. We're working in a place in a domain where labels are scarce. Sometimes the tasks, like the detection challenges, are quite difficult. And so, every project looks different. But I'll try to give a general overview of what a typical Development Seed ML project looks like. So typically we're focused on an environmental monitoring problem for detection targets that can be modeled with computer vision techniques like object detection or segmentation. Mm-hmm. So these objects should be clearly resolvable in an image and clearly resolvable as objects. We also do a little bit of time series and change detection, but a lot of our projects are focused on taking a lot of the awesome models and methods that have been developed in computer vision and deep learning and applying that to satellite imagery. Mm-hmm. So typically we'll start off with a client that doesn't have any data set, doesn't have they have an idea of what they want to monitor or map, and then we help them in the process of planning out how to annotate that data set. So how do we serve the imagery quickly to annotators so that they can create a high quality labeled data set? How do we evaluate that label quality? And then from there, how do we then package that data set into a servable format that makes it efficient to train a machine learning model? How do we provision the infrastructure, the cloud infrastructure to train that machine learning model? Because if you're not familiar, for folks listening, training these machine learning models requires a specialized infrastructure called GPUs, graphical processing units. Mm-hmm. So we assist with that. And then that's when folks like machine learning engineers like I come in once we have all of that data set and infrastructure set up to actually assist with training the machine learning models, evaluating them, And then from there, if we have a great model, then we can get into all the technology stack around serving that model, and scaling up resources based on user demand to provide model inferences that predict something in the environment from satellite imagery. That could be monitoring oil slicks, monitoring agriculture, field change, etc.
Fantastic. So you have quite a wide range of potential sort of tasks to be working on. Is it straightforward to choose a tool that will work for all of those different tasks? If you just focus on, say, data annotation, is there a tool that will annotate all the different kinds of data? Because I guess you've got optical, you've got SAR, and maybe some other kinds as well.
Yeah. It's not super straightforward. And so I'm hoping with this blog post series that we kind of captured some of the, sort of the flow chart and the decisions to sort of make in your tooling. I think depending on what detection target you're trying to map, like if you're trying to map segments, say like your object of interest is like a center pivot agricultural field, like a crop circle. In that case, like you want an annotation tool that can quickly get you like the delineated boundary of each field. Ideally, you don't want to like point and click, your polygons if you can avoid it. You want to reduce like the time per like annotated label as much as possible. So you want an annotation tool that maybe has advanced tooling, like you click and it generates a segment for you, and then you can edit that segment. So maybe it has like a simple machine learning model that helps assist you in your annotation. Maybe you need something that is active learning based, where like you want to quickly make some segments, make a simple machine learning model for your custom problem, and then have it assist you in making annotations, and it gets refined over time.
Right.
So not all tools support all those different options. And so depending on what you need, there's many options out there, and we try to help folks out with that.
And do you find that you default to the same tool each time, or does the task necessitate maybe using different tools for different problems?
Yeah, so with our stack, if we're going for segmentation, we'll use one of two tools. If we find that like it's taking a long time to edit polygon segments, like the segments are very complex, we'll look at using something that supports active learning. So we've open sourced Perl, which we've used for complexing or for annotating complex landscapes where there's agriculture, forests, shrubland, all mixed together. And so with Perl, you make some annotations and then it makes segment predictions. And so it kind of reduces some of the labor in doing vertex editing. For something like building segmentation, where it's a little more straightforward, the buildings aren't as complex in shape as forest cover or agricultural fields. We use Java OpenStreetMap editor because it has good geospatial support. We integrated a magic wand tool where you can click and generate a segment quickly. So yeah, it sort of depends. There we find that like active learning, maybe we don't need to invest so much in that, and like it's better to spend time just generating lots of human annotated labels.
All right, so that's the crux of it, getting to the speed of annotation, and sometimes there might be specific features of a tool, like a map, for example, that might speed up particular kinds of annotation. Okay, that makes a lot of sense. So you've got that point. You've chosen your tool for your data annotation. Data can be delivered in many different formats, of course. You can download a zip, or you can access through some sort of APIs. Have you managed to sort of standardize that workflow, or do you find that you also need to customize that part of the workflow?
Yeah. So for training machine learning models, like if the goal is to like train a machine learning model with the data set that you've annotated, it's good to be able to efficiently work with these large data sets. And often that requires like provisioning like cloud infrastructure that is next to where the data is stored. With these data set sizes, sometimes like they can get into the hundreds of gigabytes when you are accounting for all the imagery plus the labels. And so it becomes a little bit infeasible depending on like the clients we work with and their computing resources to download all that locally and work with all that locally. So what we typically do is we work with different cloud providers, Azure, AWS, or Google Cloud. We store all of the annotated labels and imagery in cloud storage, and then we write some infrastructure as code to deploy like our machine learning workstations to that are connected to those cloud data stores, and then we train models that way. And we try to format our data sets that we create in stack format. If clients want to prioritize that and make the metadata like really standardized and have simple APIs to access and work with the geospatial imagery and labels.
Mm-hmm. Okay, so optionally put a stack API in front of a data set and have all of that running on the client's cloud of choice for optimization of access. Fantastic. Okay, I got that. Right. So we've now annotated our data and we can access it. What's the next phase of the machine learning process?
Yeah. From there, I think the next phase would be like figuring out your data pipeline stack. So how do you go from a data set that's on the cloud, like being served over a stack in a stack API, or maybe if you didn't do that, like you're working with just cogs on a cloud bucket and loading the cogs directly from there. What does your data pipeline look like? And because like your data could be served in like these different ways, like maybe it's just cogs on a bucket, or maybe it's you have an API endpoint to a stack API. It's good to have like a data pipeline tooling that is flexible and can, I think, be adapted to these different data sources. Especially if you consider that like when you're coming up with a novel machine learning model where, with geospatial data, there's so many other data sets you can bring in, so many different vector data sets, or imagery data sets that it's good to have, I think, like a flexible data pipeline tool. So the tool that we talk about in our blog post is Torch Data. It's currently like the next generation API for loading data sets from cloud data stores or locally. It's going to support data parallelism, so you can spin up workers that can load that data, and it works well with cloud providers, and has the potential for you to describe your data pipeline graphically, to profile that data pipeline and see where the bottlenecks are. So there's a lot of exciting features in this tool, Torch Data, that I think it's going to make it easier to like get the data pipeline really correct and fast, because often like loading that data is the bottleneck when you're training machine learning models.
Yeah, I can relate to that. And is Torch Data itself, is that a mature project, or is that something that you're contributing to as well?
It's a beta project. We're not contributing commits directly to Torch Data, but Wei Ji, one of our other ML engineers, is the maintainer of a project called ZenGeo. So you can look up ZenGeo on GitHub. Its main dependency is Torch Data, and it's sort of like Torch Data pipe operators that are specific to geospatial. So you can create like a PyStack reader with ZenGeo that you give it the endpoint for your stack API. You give it some arguments that like PyStack client would take, and it returns a generator that allows you to, page through all the different items you want to load from your stack API. And the great thing about Torch Data is like the idea behind Torch Data is that it's easier to take components that have been developed for one project and bring them into your project. So a little easier to mix and match operations that are common among different ML projects.
Yeah, there's an awful lot of reinventing the wheel that goes on a machine learning project. So to hear about standardization, particularly around geospatial, is really exciting development.
Absolutely, yeah. We find we just reinvented the wheel way too much with other tooling, even just within our own team. So we're finding that ZenGeo, Torch Data are making it a lot easier just for me, myself, and the 4 other ML engineers to share and work together.
Okay, so we're now to the point where we've got, I guess, a data loader, a data generator. I'm assuming that you also use PyTorch for your model training from that stack?
Yeah, we're pretty committed to PyTorch and PyTorch Lightning for our tooling of choice for our ML framework.
Okay. And how complex does the actual training get? Do you do multiple GPUs? Do you have sort of clusters going?
Yeah, typically we try to see. Often our clients, we're running these machines on our clients, cloud instance or cloud account. So we try to see how far we can get with just one GPU and fine tuning existing models. And especially when we're in the experimentation stage, where we're just fine tuning the hyperparameters, trying to get the model to train well, and making sure that validation loss is going down, along with a training loss that we're not overfitting. We try not to deploy more infrastructure than we need upfront. Once we get to a point where we feel like multiple GPUs is going to help, train that final model that we actually put into production, then yeah, we would go to scale up to multiple GPUs.
Right. Okay. And does a tool like PyTorch Lightning make that transition from a single GPU workflow to sort of multiple GPU workflow? Does that make that straightforward?
Yeah, definitely. Like the PyTorch Lightning trainer class, you subclass that, you wrap all your data pipeline in a PyTorch Lightning data module. And from there, it's pretty straightforward to scale up to multiple GPUs.
Okay, cool. And I was quite interested in that workflow because you said that you would optimize on one GPU initially and maybe run a bunch of experiments and then switch to more of a sort of parallel approach across tools. How do you track all that, and how do you manage that sort of experiment life cycle?
Yeah, we've been using weights and biases. It's a pretty popular tool for logging any sort of metric you want to a dashboard that you can share with your team. We've really enjoyed that. We've also experimented a little bit with a tool called continuous machine learning, and that's nice. Whenever it's like GitHub Actions for your machine learning, model development. So when you make a commit with a new model, you can set up a GitHub action that then comments on the pull request with basically your dashboard output. Here's how the model did in terms of evaluation performance. And that's nice. That tool's free. Weights and biases, I think, is also free up to a certain point until you bring in lots of other users of the account. And I think there's a certain amount of artifacts you can store on that platform. So there's kind of pros and cons and to both of those tools in terms of pricing and functionality, but we've enjoyed both of those.
That's really interesting. I feel like many of these platforms do offer quite generous free tiers that will allow you to get the ball rolling.
Yeah, definitely.
Right. Okay. So we've now trained a model where we're happy with it. The next stage will be to use that model somewhere. What does that look like?
Yeah, well, once you train a model and then, if you're happy with it and you've done the evaluation in terms of false positives, false negatives, you're ready to deploy it. We have used a couple of different options. In the past, we've engineered our own model servers and integrated that with tools like ML Enabler, using AWS Batch to scale up GPUs on demand for inference jobs, on the scale of countries to run model inference, and that's worked well. But moving forward with we've found that it can be difficult to integrate machine learning engineers into the process of getting models served. And to make that easier, I've kind of been pushing us internally to standardize on torchserve, which is a project from that's in the larger Torch ecosystem. You don't really need to know a lot about Python web frameworks or anything about web frameworks in general. Torchserve has a standard model archive format. You define your handler function that says how should I pre-process model inputs and post-process model outputs. And then you have a model server that supports management, maybe you want to add new models to your server. It supports profiling, how is my model doing in terms of memory, and CPU performance as it's performing a request. So it has a lot of like good built-in tools that help you like get that model to deployable state where it can scale up and support lots of users.
Right. And then once the model is there and the services are built around those endpoints, is there a continual monitoring or optimization that takes place, maybe to reduce costs over time or something like that?
Yeah. So we worked with the Nature Conservancy on this application called Animal. And you can look it up, animal.camera. And that's animal without the second A, so ANIML, sort of a pun, ML. With that application, we were deploying a YOLO V5 model for object detection, and we're working with camera trap imagery instead of satellite imagery. But we found that with object detection running on the CPU, and we were using the CPU to like keep costs down and using SageMaker serverless to only spin up the machines when they were needed. We found that on the CPU, it was taking a long time to run inference. It was like taking up to, I think, like 10 seconds with an unoptimized model. So we helped them optimize the model with Onyx, ONNX, this model interchange format that compiles the model for a particular architecture. So we compiled it for an Intel CPU architecture, and that resulted in like really great speedups. We were then getting, I think we got like 100x speed up so that model inference was taking 4 seconds. And there's further optimizations to be done. I think Intel has their own like model specific compiler called IPEX, which we'd like to explore. Optimizing for like your architecture is a good thing to do.
Yeah. And as you mentioned, lots of new options on the horizon as well. Okay, that's been a really good introduction to the overall tech stack. I'm interested to dive into a little bit about the decision making. So, obviously, as you mentioned, lots of new tools are coming out. What's your process of maybe evaluating and then deciding if you should include in your stack or not?
Typically, we'll talk about it as a team because we each work with different clients, typically in teams of 2 or maybe even just one solo ML engineer. And so we have a diversity of perspectives on, is this tool useful in general, or is this like pretty niche? Like we would only need to use this like one-off for a particular project. So in this ML tooling blog post series, I tried to like put a lot of emphasis on tools that have been generally useful, no matter like your detection target. Is it segmentation, object detection, image classification? Whether you're trying to serve this model near real time or whether you're trying to scale up resources like on demand, or if you're trying to process batches. I see that like all these tools could be useful in a lot of these cases. Typically we just try to talk about it as a team and decide like what's most useful for the kinds of folks that we work with.
Yeah. And are there any particular requirements, say around the language that they are implemented in that also feature in the decision making?
For sure, yeah. Definitely we're as a team more comfortable with Python than say R. And we're more comfortable as a team generally with the PyTorch ecosystem. We see that a lot of new models, like transformer-based models for vision and for text, are being done in PyTorch and then published in libraries that work well with that ecosystem. Whenever we're like engaging with a new project and thinking about what model approach to look at, we generally find that like it's available in PyTorch, and we tend to go with PyTorch based solutions, if that helps answer the question.
Yeah,
we have worked with TensorFlow in the past, and we've actually come up with tutorials for TensorFlow, but definitely moving into the PyTorch ecosystem.
Right. Okay. PyTorch and Python. There are some tools and around deployment that use C++, for example, to get speed. So I don't know. Maybe there are particular situations where you would also consider other languages.
Yeah, if we were trying to run models on edge devices, like
Yeah.
we'd be looking at that more. But to be honest, we haven't really engaged with clients that are focused on those problems. Just kind of where we're typically working with is like folks want to deploy models in the cloud. And so compiling to edge isn't as, I think relevant there. But I'd love to. I could see that being done for say like wildlife monitoring. Compiling a model to run on an edge device. On a camera or something like that. I could see that useful.
Right, that's the final frontier, deploying code on device. That's an exciting place to be, I expect.
Yeah.
Well, that's been a really good introduction. I was just curious, are you happy with the stack now, or do you think it will keep on evolving, or do you see any major pain points in it that might require some additional variation?
Yeah, I'm slightly happy with the stack, but I think one pain point with like torch data right now is like profiling is not quite there. Like even though you can define all these steps in your data pipeline, it's still in kind of GitHub issue stage in terms of actually being able to see where are my bottlenecks in like the data pipeline. What's taking a long time? Is it the request to the Stack API? Is it actually loading those assets? So I would love to see profiling come along. I'm also, we're still pretty all over the place in terms of properly describing our annotated data sets. So there are various Stack extensions that can help you describe your labels for machine learning, as well as like what is the area of interest that you looked at while you were making annotations. So the ML AOI extension, and then an extension to describe your geospatial machine learning models. Where is this model relevant? What is the ML AOI it's relevant for? And those extensions are not they're not in finalized state. I think they're either in alpha or they're like proposal or they're beta. So I would love to see those advanced and get solidified more, so that more folks are using them and it becomes easier to consume geospatial ML data sets and models.
Yeah, I'm totally with you there. Let's hope that this recording is also a bit of a call to action to get some more spotlight onto those issues there. Well, Once again, thank you so much for providing this introduction and also for authoring the blog series. I assume that the best place for people to follow you would be obviously on the blog, but also I guess your LinkedIn potentially.
LinkedIn, I'm not as active on, but Twitter, RYB Avery is a good place to check out musings on geospatial ML. Also, the Development Seed Twitter, we share more posts and comms from our other ML engineers and geospatial engineers. So that's another good place to look for updates.
Fantastic. I'll put the locations in the show notes. Once again, thanks, Ryan, and I'll see you next time.
Thanks, Robin. Great talking to you.